Good evening. I'm Charles Travis.
And I am Charles Hostick, and we are here to discuss the power failure alarm circuit. This is an important electronic design. It's a widely used circuit today. There is a great chance that most electrical engineers will come across this during their career.
The purpose of a power failure alert circuit is to warn of voltage drops or send a continuous alarm or specified actions in the case of a catastrophic power failure so that action may be taken. Transistors and MOSFETs can be used for switching in circuits such as the power failure alert circuit. In the 1970s, the use of switches and integrated circuits ramped up, and transistors are now some of the most used components in integrated circuits. When a power failure has been detected, the system needs to alert the operator through visual or audio means such as an alarm or indicator light. In a more complicated circuit such as a logic circuit, it could simply put out notifications or shut down the system completely, as well as power up generators or other safety equipment. Power failure alert circuits are a major part of critical equipment design in which power failure would have devastating consequences, such as in the medical field, aviation, and military applications. This circuit in some form can be found in many products and may be as simple as alerting a user to a low battery in a phone.
So here's our circuit under power, and it's receiving power from this power supply V1. Power comes around to this diode D1, which will be on because we have voltage at the back and no voltage at the front. It will come through here to the capacitor, charging the capacitor, and of course that will complete the circuit back around to the power supply. Now, what's happening with Q1 here, the transistor? What's happening to that depends on the voltage at the base, or the difference between the voltage at the emitter and the base. Now the base voltage is controlled by R1 and R2, the proportion between the two. R2 isn't that important, the size of it, but R1 is as far as the proportion to R2. At 750 ohms, you can see here the base voltage is 14 volts. The emitter voltage is 14.5 volts, so the difference is only 0.5 volts. At 0.75 is when that opens, this diode right here between the emitter and base, so that's off. And of course, C has got no voltage, so the difference between B and C makes this diode off as well. Now, one thing to note is that if you make R1 too large, the voltage here at the base will actually drop too far, and even under power, it will turn this transistor on and the buzzer will sound. So that's something that we had to work on to make sure we knew what R1's value needed to be to keep the buzzer from sounding under power. You'll see on our project that we'll show later in the video that there is a potentiometer in place of R1, and we use that to demonstrate the variable resistance to determine what resistor we needed in our actual circuit. Here's our circuit in power failure. We've opened the switch to indicate just that. The voltage at the back of D1 will be effectively 0, so D1 is off, and there's no voltage flowing through there. And the capacitor, which was fully charged when the circuit was charged, will start to discharge back towards the emitter, and the voltage between the emitter and the base will indeed be 0.75 volts, which will allow this diode to be on. This diode here will continue to be off, so it's an active mode, and the voltage and the current will flow across the emitter collector base with a drop, of course. That voltage and current will drive this buzzer until the capacitor is completely discharged. Now, instead of using a capacitor, we could have used a battery source or some sort of logic circuit. that would have taken, the battery source could have let the buzzer last longer, or you could have a light, but the logic could do many different actions, whatever you've designed it to do, to take place when there is a power failure. Here on this breadboard in the forefront is the circuit we built. Right here, this potentiometer is what we used in place of R1 so that we could test different resistances, and that was kind of fun to play with as we determined the actual ohms that'll work best for this circuit, which was around 500 to 750. In the background, you'll see an L shape there is a 3D printed radial to linear motion machine driven by a DC motor, controlled by a motor controller. That is merely just going to serve as our load. Looks cool, but we could have hooked up anything there. And the circuit, you'll see as it charges and is ready, is unaffected by that load. Now, what we're going to do next is show you a video to show this circuit in action.
This is a demonstration of our power failure alert circuit. At this point, we'll turn it on. We can see the load is running in conjunction with the power failure circuit. The motor itself can be powered down without any worry of setting the alarm off because it is fed power from the same source as the power failure alert circuit. When the main power source has a voltage drop, the alert circuit creates a warning chirp. When the power source has a failure, the charge capacitor drains across the buzzer to alert that a failure has occurred.
In conclusion, power failure alarm circuits are an important electronic design in wide use today. There's a great chance that most electrical engineers will come across this important circuit during their career. Thank you and have a great evening. Are there any questions?